and welcome to exercise 9a, the solution. So in 9a, we want to calculate the probability that the first arrival arrives before some time t1 and that the second arrival arrives before some time t2. And in order to calculate this, maybe it's a good idea that we just start by writing up some of the things that we know. So one of the things that we know quite surely is that the arrival times are probably not that fun to work with because t2 is the sum of two exponentially distributed random variables, so we'll have to do some convolution. t1 and t2 are not independent, and that's not nice as well. So we want to work towards somewhere where we can work with independent random variables at the least. So let's just recall what t1 is in terms of the inter-arrival times. So in terms of the inter-arrival times w, t1 is just equal to the first inter-arrival time because it's just the time that passes between time 0 and time t1. Now the second arrival, it arrives at time t2, and that is given as the time that passes from the 0th arrival to the first arrival plus the time that passes between the first arrival to the second arrival. Now this is nice to write up and use for several reasons. First of all, we know that both w1 and w2 are exponentially distributed with parameter lambda, by assumption in this exercise. Second of all, we know that the inter-arrival times are independent. So w1 and w2 are independent. And in particular, this will allow us to acknowledge that the joint density of w1 and w2, which I will just write like this, the joint density function can be factorized into the marginal densities because of their independence. And the marginal densities are just the densities in an exponential distribution with parameter lambda. So this is the first marginal density, and then we have the second marginal density. And this is a very attractive thing to realize because essentially it means that the probability that we want to find, this thing here, can be sliced and diced into something that's more easy to work with. So this is the same as the probability that w1 is smaller than or equal to t1, and that the second arrival, which is given as w1 plus w2, is smaller than or equal to t2. Now, we can just move things around a little bit here because we kind of want to think of this in terms of w1 and w2. So I need to let w1 be smaller than or equal to t1 first and foremost, and then we have w2 that must be smaller than or equal to t2 minus w1. Yes? And now essentially what I just have is I want to calculate the probability of an event that relies on two stochastic variables. And how do I do that? Well, just good old probability theory, I need to integrate over the right set to find the probability of this event here. Now, first and foremost, what we see is that w1 has some quite clear limits because w1 is exponentially distributed, so it must be greater than 0. And we want to find the probability, among others, that it's smaller than or equal to t1. So we integrate with respect to w1 from 0 to t1. And the thing we're going to integrate, since we want to find the probability of an event that relies on w1 and w2, we will integrate with respect to their joint density. Yes? So the inner integral that we need here is we're going to integrate with respect to w2. Again, the lower bound is 0 because w2 is an exponentially distributed random variable. And the upper bound, well, it's actually given here. For different values of W1, the upper bound is just T2 minus W1. And this, again, by using the independence of the inter-arrival times, this is equal to lambda multiplied by e to the minus lambda W1, and lambda multiplied by e to the minus lambda W2. And then integrate with respect to W2, and then I integrate with respect to W1. Okay. So we're actually more or less there now, because what we get now is, well, just straightforward calculations, right? I can take the lambda outside. I have e to the minus lambda W1 here. And then what I will have to do is I have to integrate lambda e to the minus lambda W2 with respect to W2. And the antiderivative of that is minus e to the minus lambda W2. And I will evaluate it in 0 to 2 minus W1. And I have to integrate all of this with respect to W1. And basically what I see is the inner integral, it integrates to 1 minus e to the minus lambda T2 minus W1. And this gives me two integrals. The first integral is lambda multiplied by the integral of e to the minus lambda W1. With respect to W1, integrate it from 0 to T1. And that is just lambda multiplied by the antiderivative, which is 1 over lambda with a minus here, e to the minus lambda W1. Take that antiderivative from 0 to T1. And then I subtract lambda multiplied by the integral from 0 to T1 of e to the minus lambda T2, and then I also have e to the minus lambda W1, but that cancels with the e to the minus lambda W1, so here I just have this thing. And since the integrand does not depend on the integrator, this integral is just the integrand multiplied by the length of the interval. So in the end, what I get is I have 1 minus e to the minus lambda T1 minus lambda T1 e to the minus lambda T2. And that is what I get as the expression for the probability that the first arrival time is smaller than T1 and the second arrival time is smaller than T2 for T1 less than T2. Okay, so that was one way to calculate this, and very straightforward. Now I would like to present you guys for one more way of calculating this, because you have probably seen the solution for this week uploaded in PDF format at some point. So let's just, I'll just write the result out here, okay, just so that we have it. The result is that the probability that the first arrival is smaller than equal to T1 and that the second arrival is smaller than equal to T2. That probability is given by 1 minus e to the minus lambda T1 minus lambda times T1 e to the minus lambda T2. Okay, so that was one way of doing it. Now I would actually like to show you people okay, great. I would like to show you guys one more way of doing this, just because it's nice to work a little bit with conditional expectation also. So if you look at the PDF solutions that have been uploaded, you will see that there is something with some sort of conditional expectation somewhere in there. And that is what we will take a look at now. So we work in the same setup as we did in the beginning, where we still make the same observations with respect to the inter-arrival times, right? But now let us try to do this in another way. So method number 2 is we condition. Yes. We condition on what? Well, let us try to condition on W1, because that's what they do in the PDF solution. So we say, we take the probability that W1 is smaller than or equal to T1, and that W1 plus W2 is smaller than or equal to T2, and we condition on W1. Now, by the double expectation property, this probability up here is the same as if I took the expectation of a conditional probability inside. Now, what is the next step? Well, let us try to take a look here. There are some things that we can do. First and foremost, let us always keep in mind the correspondence that there exists between the mean of an indicator and the probability of the event that the indicator indicates. So basically what I've written here is a double expectation, yes? Or the inner conditional expectation is the conditional expectation of the indicator of W1 being smaller than or equal to T1 multiplied by the indicator of W1 plus W2 being smaller than or equal to T2 given W1. Now, I would also just like to pinpoint here that when I say that I split this indicator up into two indicators, it has nothing to do with independence. Just completely in general, the indicator for an intersection of two events is equal to the product of the indicator for the first and the indicator for the second. That always holds, no matter if you have independence or not. Think a little bit about this and you will realize that it is true. Okay, so what we're going to do now is we're going to look a little bit at, if I can find the color, we're going to look a little bit at what we can move outside of the inner conditional expectation. So there is a conditional expectation rule that's called moving out what is known. And basically, so you can see this on the conditional expectation cheat sheet I gave you guys. So basically this means that when I condition on W1, then if I have something in my expression inside here that relies on W1, then I can factor it out. Yes? I can't really do it here with the second indicator because W2 is also in there and it's creating noise. But the first indicator, it relies only on W1. So because of the moving out what is known conditional expectation calculation rule, I can move out this indicator of W1 being smaller than or equal to T1. And that's kind of nice because then I just have something inside here that I can kind of treat on its own if that's what I want to do. Now here's where the fun part kind of begins, because what do we do here, right? It's kind of hard to just say we're going to do this or we're going to do that, because to be honest, we have no fundaments that can tell us exactly how are we supposed to act when we want to find the conditional expectation of a function of two stochastic variables conditioned on one of those stochastic variables. Except, well, not completely true. We do have a rule from insurance and law that tells us how we should calculate this thing here. So I'm just going to write up the expression for you guys in general first. Let's see. I'm going to use my notes here just to make sure that I don't write something wrong. So the expression in general is this. If I want to find the mean value of some function of x1 and x2, given that x2 is something, concretely some value, well then that is given as the integral over the real axis of g of little x1 comma x2 multiplied by the conditional density of x1 given x2 integrated with respect to x1. Yes? So this is something that's kind of good to remember, because this is one of the rules that we will use now as we calculate this entire expectation expression. So I want to find the expectation here of whatever is inside, and which distribution lies behind this expectation. Well, the thing that is stochastic here is the W1. So the density that I need to use here is the density, the marginal density of W1 that I will integrate with respect to. And W1 lives on 0 to 1, 0 to infinity. However, I also have the indicator here that W1 needs to be smaller than equal to T1, so I integrate up to T1. Now inside here, what I want to do is I want to integrate over all of the values that this can take. Yes, for W1 as such. And now we can implement this formula that I had written on the side to write up what this expression should evaluate to. So this expression is, so now I will use the formula, and to signify that I'm using the formula and that we're working on an inner integral here, I will use this color here. So what I'm conditioned on is here is W1. So what I will have to integrate with respect to is W2. And let's just say that, well, we're integrating with respect to W2, and W2 has support on 0 to infinity. So let's just use that for the moment. Now, the G function in my case is this indicator function saying that W1 saying that W1 plus W2 must be smaller than equal to T2. Now, since I'm integrating with respect to W2, it's nice if I can kind of isolate W2 inside this indicator. So I will write the indicator that W2 is less than equal to T2 minus W1. And then I have to multiply by the conditional density of W2 given W1. Yes? Now the conditional density, let us just recall what that is. That is the simultaneous density. And well, let's just write W2 given W1 here, just so we know that this is the conditional density, divided by the marginal density of W1. And since W2 and W1 are independent random variables, this conditional density is just the marginal density of W2. So I can just plug that in, right? So let's just continue working on the inner integral here. The inner integral, I can also see that I am integrating on an indicator where W2 has to go up to T2 minus W1. I integrate with respect to W2, and what I integrate is just its density. And then I have my outer integral, which is the integral from 0 to T1 of the density of W1, and I integrate with respect to W1 out here. Okay, so we can see that actually, basically, I've already arrived at the expression that we had earlier. when I used my own our own first approach. Yes, but just for fun's sake, let's try to calculate this so that it kind of looks like what we have in the PDF solution. So the thing that's inside here, what are we looking at? Well, we're integrating the density over a set. So this is exactly the same as the probability of W2 lying inside that set. So the probability of W2 being smaller than equal to T2 minus W1. Yes? And that is also exactly equal to 1 minus e to the minus lambda W2, where this is the distribution function in the exponential distribution. And please look that up if you cannot recall that. So because of this, basically where our calculations are now is we have to find the integral from 0 to t1 of the density of W1, which was lambda e to the minus lambda W1, and then multiplied by what the inner integral ended up evaluating to. Oh, sorry, I think I wrote this wrong here. This is supposed to be T2 minus W1, right? That's just my fault. So T2 minus W1. Then with respect to W1. And if we do these calculations, and we actually finish these calculations, we end up with exactly the same result as in the first case, where we just calculated in another way, which was 1 minus e to the minus lambda t1 minus lambda t e to the minus lambda t2. So those were two different approaches. I hope the second approach wasn't too confusing for you guys. It was mainly, I mainly used it so that you can kind of use this to fill in some of the gaps there might be in the PDF solution, so that you can just kind of recognize some of the things that are there and some of the things that are here. So this was the solution of 5A, and then you might say, wait a second. In 5A, we also need to find the probability that the first arrival comes before time t1, right? We also need to find the probability that t1 is smaller than or equal to little t1. What about that one? We haven't calculated that yet. But the thing is, we have calculated something that is more intricate, which is the joint distribution function of t1 and t2. So in order to find the distribution function of t1, all you have to do is plug infinity into t2's place in this expression down here. And as soon as you do that, the last term will cancel out. So basically, we have answered both the first and second part of 9A. So that was 9A, and in the next one, we will look at 9B.